Now let's move on to ionic compounds, right? So ionic, we said, is a metal and a non-metal. So metals being on the left side of the staircase and non-metals on the upper right part of the periodic table. So when we have them together, we call it an ionic compound, and we have a different way to name them. Anyone know the formal name of the first thing here?
Sodium chloride.
Yeah. We eat that constantly. You need it in your diet or you die, because they are both important ions for making your muscles, your brain, your heart. Like everything important works off of sodium and to a lesser extent chlorine. Ions, by the way. Don't eat plain sodium, you'll die. Or at least end up with severe burns. All right, so what's the next one called?
Calcium chloride.
Easy as pie. We do not use the prefixes with ionic compounds, ever. It's a rule. It's actually a rule decided on by the organization that determines the rules for naming all things, which is called the International Union of Pure and Applied Chemistry. They make all the rules about measuring and naming and all the stuff that we learn in the first month of chemistry, essentially. All right, how about the next one? Anyone know what Mg is?
Magnesium Fluoride.
Yep. So, why do you guys suppose we don't need to use the prefixes for ionic compounds? Anyone have a guess? Why aren't we saying how many chlorine are there? Yes. So covalent compounds have essentially an unlimited number of proportions that they can form. Ionic compounds, not so much, because it's based on the charge of the cation and the anion. So you're going to learn in the videos that I left up for you yesterday. Cations are positive, anions are negative. So here, sodium is always a +1, which means it can only have one chlorine attached to it because it's always a -1. These are the ions, not the elements, okay? So those are two different concepts. So by inference, tell me, what does calcium have typically? What charge? Yeah, Matthew's got it, because it has to balance out, right? So what I mean by that is if you have two chlorine and each one is worth a -1, you have to have a +2 to balance that out, because your charge on an entire ionic molecule is 0. So here our X represents the charge calcium has. So you can also get that from the periodic table, because calcium is in group 2 and all group 2 ions are +2. Sodium is in group 1, so you might be noticing a pattern. It's an important one. All right, so like by inference again, what charge do you think the magnesium has? Oh, yep, Kyle got it already. You anticipated my question. All right, so the reason we don't need the Greek prefixes is because the number of anion are sort of attached to that ion is limited by the charge of the ion to begin with, of the cation. So it would be kind of redundant, essentially. All right, so tell me, what's the first name here, this guy? Or girl, I don't know, I didn't ask. How about the next one?
Iron oxide.
The next one's LOL. Ooh, we found the trick. Are these the same thing? As it turns out, no. All right, this one is red. It's mostly what makes Mars the color that it is. It's rust. You have seen it on the fenders of every Ford in New York State. Just kidding. Most of them. Iron oxide here, this is rust also, but it's black, and it's much less common. Also rust. They're both products of oxidation, so we call them rust. But they are different. They have different physical properties, different solubilities. Okay, Erin, so you're going to need to touch base with your group and get some notes.
All right, we'll do.
What was I saying? I forgot. Okay, so iron oxide and iron oxide are clearly not the same thing because they have different colors, different properties, different solubilities, all kinds, different melting points. Everything is different. So now we have a conundrum, and the only way to solve it is to indicate which version of iron we have. So if you have already picked up the green periodic table from lab, if you didn't get it, ask your lab professor. But if you have already picked it up, you can look at it and you'll see that at the top, I think it's on the right corner, you'll see a +2 and a +3 for iron. Those are the possible charges that it has most commonly. So one of these is +2 and one of them is +3. Which is which? We're done in 10 minutes anyway, Matthew. Yeah, how did you get that? This is Fe3+, which we would write as an ion like that. But in the name, we're actually going to write it as the Roman numerals, just like you typed it. Like so. There might be a version online, Kyle. Shoot me an email and I'll try to upload one for people. It's a good idea to have it anyway. But the one in person is durable and useful, and it has some info on the back that's also handy to have. So grab it whenever you're in lab next. All right. That one's okay, Casey, but there are better versions that are more printable. So this is iron 3 oxide. You'll notice there's a space between, but the Roman numerals are just applying to the iron. And we get to that because the oxygen, the only charge oxygen has on your periodic table is a -2. And so -2 times 3 is -6. And you have 2 irons. So that charge needs to be distributed between the 2 iron, and it needs to be the opposite. So that's how you get to it. It's a little bit of algebra. If you wanted to do it as a normal series of equations, it would go like this: 2 times whatever iron is plus 3 times oxygen equals 0. Either way. And then over here, what are we going to write for our Roman numerals on the second version? I'm actually going to rewrite it. So if this is 3, what's this one? Tablet. Table? There is no iron 1. Well, iron 1 is uncommon. It happens in biology, but it's complicated. Mostly we get 2 or 3. And this is iron 2 because the oxygen is only ever a -2. So having that periodic table handy to see what your options are is good. And the basic idea is when you look at the periodic table, if there's more than one charge on the metal, you need to use Roman numerals to show which metal you're actually talking about. Lowercase e is F little e. Okay, so here's the rules for binary compounds. Let's see if we can apply them with these examples here, and then we'll be done for the night. What do you want to call the first one? Anyone know what Cu is? Oh, Matthew does. It is copper 2 chloride. So if you look at copper, you have a choice of +1 or +2. So that means they're both common. We know that it's 2 because chlorine is always -1, and there are 2 of those. It's kind of by inference, Kyle. So you want to look at what it's attached to. So if it's attached to a chlorine and there are 2 of them, that's going to be worth a -2 total for your anions. So your cations have to balance that out. Okay, so it has to be a +2 in this case. That's a good question. All right, let's try silver. Oh, damn it. I just gave it away. That was awful. Not silver 2, because silver 2 would have 2 chlorines here. Platinum 4 chloride is that one. But that's not the symbol for 4. Somebody help him out. What's the Roman numerals for 4? Yeah, like that. So silver doesn't have a choice. You could say silver 1 chloride, but if you look on there, on that periodic table in the upper right corner of the box, it just says +1. So you can also just say silver chloride because it doesn't have any other option. You should know Ag. We're going to keep running into it. Platinum is my personal favorite. It's what I did my graduate work on. So platinum with 4 chlorine attached to it is platinum 4 chloride. I'm running out of space. Okay. All right, so this is just an introduction. How do you think you're going to get really good at naming stuff? By me showing you how to do it all the time, is that going to work?
By studying and practicing.
Yeah,
Practice.
Alex.